Good afternoon, everyone. I'm Shashank, and I'm a fourth-year PhD candidate working with Professor Reza Moini. Today, I will be talking about tough and ductile nacre-like cementitious composites. So there will be a lot of conversation about fracture toughness of this nacre-inspired material. A key challenge in cementitious material is their inherently low fracture toughness and tensile strength. Although they perform well under compression, their fracture toughness are limited, leading to sudden failure under tension for a cement paste and in a quasi-brittle fashion for a concrete material. This is due to limited ways for concrete to dissipate energy under tension, and this is limited toughening mechanism in the fracture process zone of the concrete, like micro-cracking, crack deflection around aggregate, crack bridging, and crack closure induced by surface toughness. So because of these limiting toughening mechanism, not surprisingly cementitious material lies in the bottom left of Ashby plot that shows a relationship between fracture toughness and tensile strength. So the question we ask is, how do we engineer toughening mechanisms so that we can improve the fracture toughness of these cementitious material while maintaining the strength? Another challenge with improving any type of mechanical property is that there lies a mutual exclusivity in these engineered material. If you try to improve the fracture toughness, you see a drop in other mechanical properties like stiffness or strength. However, biological material seems to have overcome this mutual exclusivity by increasing the fracture toughness while maintaining their strength or stiffness. So the reason they do overcome this mutual exclusivity between the strength, stiffness, and toughness is the design, is the internal design of their material, also known as architecture, internal architecture that helps them to improve their fracture toughness while maintaining this strength. So talking about these multiple design, nature provides us with several design motifs, and these two sessions we have seen several of these design motifs from Bulligan, double Bulligan, sinusoidal, tubular, and but I will be focusing on something layered, something that is inspired from the abalone shell. So nacre. Nacre is also known as mother of pearl. It is well known for its exceptional resiliency and remarkable fracture toughness. It's also known as nature's armor. So it gets its high fracture toughness because of this brick and mortar architecture, in which these bricks are made up of aragonite crystals, and there's a thin biopolymer that basically takes the space between these brick-based systems. Because of this brick-mortar architecture, the nacre is able to withstand extreme toughness and show fracture toughness that is 3 orders higher than its constituent materials. So how does it do that? So nacre achieves this remarkable toughness through combination of the toughening mechanisms. Key processes include sliding of individual tablets, energy dissipation through viscoelastic deformation of polymer interfaces, interlocking of the tablets, and the presence of the nanoasperities on the tablets. These mechanisms, they work together to spread the damage in a wider area, creating a staggered crack path and prevent sudden failure. So in our research, we have adapted this concept by focusing specifically on the sliding mechanisms of the tablet. We hypothesized that promoting tablet sliding within a brittle cementitious matrix could help spread the damage and increase energy dissipation, leading to enhanced fracture toughness. So now the question is, can we achieve nacre-like inspired toughness by allowing controlled sliding of tablet within a brittle matrix, and how do we do that? So our approach is, we create these tablets. We start with a simple hexagonal tablets. We just focus on the tablet sliding mechanism, and we introduce a soft material that is polyvinyl siloxane in between these layers. And we characterize the fracture toughness of these material using SENB test, and also we look at the resistance curve to see how the crack propagation behavior happens in these type of material. So to fabricate the sample, we have used a lab-grade laser to groove a thin layer of cement paste with these hexagonal designs. You can find more details in our paper. We have also allowed for an offset between two consecutive layers. As you can see, that there's a 15 millimeter offset between these two layers, so that it allows for more tortuous crack propagation rather than a straight crack propagation from the bottom layer to the top layer. So we have fabricated three types of sample. The first is layered, where there's no laser grooving. The second is the Nacre-like groove sample, where we have partially grooved these tablets by up to 70%, 75% of their depth. And the final samples are basically Nacre-like separated, in which all these tablets, hexagonal tablets, are separated. In between each layer of these platelets, or the groove platelets or separated platelets, we have a thin layer of a polymeric interlayer, which allows for the shear transfer across the layers of the sample, and allow for the sliding and the avoid for the tablet failure, and allows for the sliding of these tablets under tensile loading. We have also did sensitivity analysis with the size effect, but I am not discussing it for the sake of time today. We'll be getting to the main results. We also have explored the interfacial strength and fracture toughness using different type of test setups, and we found that the shear strength of the interface is statistically higher than the tensile strength, and similarly, the mode 2 or the shear fracture toughness of the interface was higher than the mode 1 fracture toughness. So, getting to the main results, here I'm showing a load displacement plot for a 3-point bending test of cast, layered, and Nacre-like groove and separated sample. The cast samples, it failed in a brittle fashion. It reached a peak load and there was a failure. However, all the other three samples, they showed a ductile failure, which shows more control over the control failure compared to the brittle cast. In terms of strength, the Nacre-like separated has a statistically similar strength to the cast. However, the strain at failure, which corresponds to the strain at the first peak of the load displacement plot, we see that there's a 19 times higher strain or displacement in the Nacre-like separated samples compared to the cast. I also want to focus on one more thing. These dotted line, this shows the failure post the cement failure. In the Nacre-like separated sample, there was no failure of the cement paste because the crack propagated through the separated grooves rather than through the cement paste tablets. Looking at the fracture toughness, where we have a notch, and we did a 3-point bending with a notch sample, we got a similar load displacement plot. The crack initiation fracture toughness, this corresponds to the initiation, the fracture toughness required for the initiation of the crack, was statistically similar for all the samples. However, the crack propagation fracture toughness is increased by 17 times in the Nacre-like separated sample compared to the cast. So we have introduced ductility, and we have transitioned these weak cast samples to tougher ductile samples. We also see that there's a very late onset of previous layer failures in these Nacre-like separated material. So that's delayed failure also provided additional ductility in these Nacre-like samples. Looking at the resistance curve, which shows the fracture toughness against the crack extension, we see that for the cast cement paste, there was no resistance for the crack propagation, hence we have a straight line. For layer sample, we see a slightly staggered fracture. This staggered increase in the fracture toughness increased for the case of the group sample. However, for separated sample, we see a smooth rising arc curve, which alludes to the hypothesis that we had a lack of brittle fracture of the tablets, and there was tablet sliding that was being generated by the viscoelastic interlayer material that is present there. To understand the crack propagation better, we also looked at the DIC and micro-CT results. So here is intact sample for the Nacre-like groove, and this is the DIC at the first previous failure, basically correspond to this point in the load displacement plot. So you can see in the Nacre-like groove sample, there was some local strain, there was some strain localizations in the interlayer, even before the sample reached the peak load, which basically corresponds to the energy dissipation in the previous interlayer. Once the sample is cracked, you can see the crack followed a very tortuous path, and there were multiple cracks in the samples. As you see in the micro-CT that shows the 3D crack, this crack deflected across the grooved, the grooving that has been done by the laser, and also partially goes through the tablets itself. For the Nacre-like separated sample, though, what we see is that there's a more pronounced deformation in the interlayer at the same load as compared to the Nacre-like groove sample. And following the cracking, we see that there was in the DIC, you see the crack propagated in mostly straightaway fashion, but when you look at the micro-CT, you can actually see there was quite a tortuous crack path that follows the interface between these tablets rather than going through the tablets themselves. So basically, what we see is tablet sliding mechanism that I was talking about in nacreous material. Looking closely to the crack propagation in Nacre-like groove sample, you can see the crack, there is this viscoelastic deformation, the crack propagates in a tortuous path, and there are multiple spots where the crack initiates as well. So the damage is spread out all over the sample rather than focusing at the one single point. Similarly, with the separated sample, you see there's quite a lot of interlayer deformation, and then the cracks start nucleating at the multiple points, and finally all these nucleation merges with one single crack that propagates through these interlayer interfaces between these tablets. So the design leverages crack deflection to enhance the toughness and prevent a brittle failure. So now talking about the HP plot, coming back to that, we actually increase the fracture toughness with these Nacre-like material by one order by maintaining the strength. And this Nacre-like separated case specifically shows fracture toughness as comparable to the ECC and UHPC that is well known for their high fracture toughness. So in conclusion, we are envisioning a concrete as a new type of cementitious composite here. And we are focusing on one mechanism at a time approach where we just focus on the tablet sliding in the tablet sliding mechanism in the Nacre rather than focusing on the multiple mechanism that we see in Nacre. And advanced manufacturing can enable this new design. We have used laser processing and lamination. However, there can be multi-material 3D printing that can be used to fabricate these type of samples in future. And fracture toughness as high as UHPC can be obtained by this type of architecture. Other use of the laser is this our group playing a laser tag. Also talking about more my group and going back about all these architected designs that we can explore. We are exploring them in lab in the cementitious material like double bulligan, vascular cellular that my colleague Lara will present on Tuesday, and Nacre, and my another work is bone-inspired tubular, shell-like sinusoidal, Eamon's work on interface and interlocking. So, yep, That's my work. It's been out there in advanced function material. We made it to the back cover recently. So yeah, thank you.